but we're still respecting it for the seminar, starting at 07. So it's a pleasure to have Brian LeRoy with us. Brian is very well known to certainly some of our members because he did his PhD here at Harvard with Bob Westerfeld. He did very interesting experiments using scanning gate microscopy to look at two-dimensional electron gases. Then I first met Brian in Delft. I was a graduate student back then, and he was a postdoc in a group of Case Taker. He did very interesting STM experiments on carbon nanotubes while at Delft. In fact, he was the first one to image suspended carbon nanotubes. So you can imagine how hard can it be to land with an STM tip on a nanometer object which is hanging there suspended, and then do imaging spectroscopy there. And then after Delft, he moved to the University of Arizona, where he has been a professor ever since. Brian has done a lot of very interesting work. He's a good friend and collaborator of mine. We did together, but it was both in his lab. A lot of imaging of graphene on hexagonal boron nitride. And the first experiments demonstrated Moiré patterns on graphene on hexagonal boron nitride, and the modification of the electronic structure of graphene on hexagonal boron nitride were done in his lab. And these are experiments we have now, seminars and very widely known. And he continues to do great research, mostly with scanning tunnel microscopy techniques. And he's going to talk about very interesting experiments on twisted van der Waals heterostructures. So we're looking forward to listening.
All right, thanks, Pablo. Thanks for the introduction. It's good to be back here. It's changed some of Bob's old lab got chopped off and added a new building since I've been a student, but it's still recognizable here, and so I'm glad to be back and tell you a little bit about what my group is working on. So as Pablo said, my group uses scanning probe microscopy to study electronic properties of materials, and so this can be everything from carbon nanotubes to looking at quantum dots in those. These are semiconductor materials, looking at the band structure with Fourier transform STM measurements. Here's the experiment that Pablo talked about of landing the nanotube, the tip on the suspended nanotube. But what I want to tell you about today is stuff that's happening in graphene heterostructure. So what happens when you make heterostructures involving graphene? And so, as I don't think I need to tell everyone, graphene is a semi-metal here. We have these Dirac cones. And it's an interesting semi-metal, but the idea is to see what other more interesting things can we make besides just having the usual Dirac spectrum here. How can we modify this? And so we're going to do that by using this whole range of other two-dimensional materials. So we have graphene, which is going to be our semi-metal that we're going to be probing. And then the idea is to couple it with a range of other materials. So we can have everything from semiconductors, if we use things like tungsten selenide or molybdenum sulfide. We can have metals or superconductors, niobium selenide, other ones like that. And then insulating materials. So I'm going to talk quite a bit today about what happens when you couple graphene and boron nitride. And so this is a material with the same lattice structure as the graphene, but instead of having carbon atoms, you have boron and nitrogen. And so the asymmetry there gives a large band gap. And so these materials all have one thing in common with each other, which is that they have strong in-plane bonding and weak out-of-plane bonding, so that we can isolate them down into, in the case of graphene, monolayers. And for the rest of the materials I'm going to tell you about, they just need to be thin materials, and we're going to look at those. And so this is then sort of the picture of what we want to do. And what we've been doing in my lab for now, I guess it's almost 5 years, taking graphene and coupling it with other materials, kind of like Legos, and seeing what kind of new functionality we can enable by mixing and matching these materials together. And so a lot of that work has been done, thankfully, by Pablo in terms of the fabrication of making these devices through all their collaborators. And then in my group, what we're mostly interested in doing is actually then probing these materials using scanning tunneling microscopy. So this is the system that we use here. It's a low temperature, so everything I'm going to show you today is done at 4 Kelvin, ultra high vacuum STM. And so the action is happening inside here. We have our tip, and we have our sample up above. The sample is fixed, and then the tip is scanning, and we're doing then our measurements at low temperature with the ultra-high vacuum to try to keep everything nice and clean inside. And so we're going to operate in two different modes. So I'm going to show you lots of pictures today of topography and spectroscopy of these systems. So let me just quickly go through this in case anyone is not familiar with how we do these measurements. So in a topographic mode, we're basically we have our fixed sample, we bring our tip, we bring it very close, and then the tunnel current you get is exponentially sensitive to the tip sample separation. So that's the term out in front here. And so any changes in the tip height give an exponential change in the current. And so using a feedback circuit, we just keep the tip current fixed as we scan the sample. And so the tip then just adjusts to the surface profile. And using that feedback, then we get a map of the topography. And so this allows us to see where the atoms are sitting on the sample and learn about something about the morphology of the sample. But what you can see is it doesn't only depend on this e to the minus z over z naught. There's also this integral over the density of states of the sample. And so there's also information about the electronic properties of the sample. And the way we isolate that is instead of scanning our tip over the sample, we go to a fixed location in the sample. So we sit at some fixed location. We turn off the feedback circuit that we're using to keep the tip current constant, but we then keep the tip height constant, and we measure the changes in current as we change this voltage here. So we change the voltage between the tip and the sample, and that allows us to tunnel in to different states in the sample. And so these are plots here of di dv. This is going to be proportional to the density of states as a function of energy or tip voltage here. And so what you see here, this is a typical di dv curve for graphene. We have this linear dispersion here that's coming from these Dirac cones being linear in momentum. And so we're getting di dv information which is proportional to the density of states in the sample. So we have these two modes, a topographic mode and a spectroscopic mode. But really with the STM, we can also combine these two modes together. And so we can actually take this topographic mode and do the spectroscopy at every position, and that'll give us information on a spatial map of the local density of states. And so what you see here is in the top image, this is the topography where the atoms are actually sitting. And if we go and zoom in here and look at the density of states of the sample, it also has some periodic modulation to it. And if you were to look at these two closely, or take a Fourier transform of them, you would find that the periodicity here in the density of states does not actually match the topography. So there are some other periodicities going on in the sample. In this case, it's from some kind of scattering in the sample. And so we can learn something about the band structure of the sample by taking these images where we do spatially resolved density of states measurements and looking at how the wave vectors differ from just the atomic lattice. And so those are the three types of measurements I'm going to show you today: topography measurements, spectroscopy, and also a little bit of these density of states measurements. And so what I wanted to tell you about today is two different stories of enabling new functionality in graphene, and doing that by either combining graphene with an insulating material. So in this case, this is going to be graphene on boron nitride, or what happens when you combine graphene with itself. And so this is twisted bilayer graphene, two sheets of graphene on top of each other with a, in this case, a very small twist angle between them. And so let me start with the story of graphene on boron nitride, graphene on this insulator. So almost all graphene devices from all the way from the beginning, when they were first exfoliated, were started on graphene on silicon oxide. And so the reason for this was silicon oxide is a good substrate to be able to see graphene. You can identify it through optical contrast. But when you actually go and do a transport measurement here, look at conductivity as a function of gate voltage, you see it takes a rather large gate voltage to change the conductivity here. And that's because, well, first, the oxide is relatively thick, but also there's quite a bit of disorder in these samples. So there's a lot of disorder in the graphene that's coming from the substrate. This is work from the Jacobi group looking at the fluctuation in the silicon oxide. So the charge density fluctuations there under these devices, and you can see it's on the order of 10 to the 11 electrons per square centimeter. So this graphene monolayer that you have sitting on there has these fluctuations of like 10 to the 11 per square centimeter in the density in it. And you can also go and look at this. This is on the sort of micron scale. If you go down and look on the nanometer scale, you see the same thing. There's a strong disorder in the silicon oxide substrate, and it's coming from the impurities that are trapped in the oxide. And so to get rid of this, we wanted to use a different substrate. And so the original idea then was to then try to use something that we could be better matched to graphene. And so this is work from Philip Kim and Jim Hohn's group using graphene on boron nitride. And so the idea of this experiment was we wanted a better substrate. Ideally, it would have all three of these conditions, be atomically smooth. So the silicon oxide I showed you before has typical roughnesses of something like a ½ nanometer. Here's an AFM of silicon oxide. So it's not a particularly flat surface for the graphene. But more importantly, there are many charge traps in there. There's dangling bonds on the surface of the oxide. And so that's not really what you want if you're going to put your graphene right on top of that. And the third requirement is that it's an insulating substrate. So silicon oxide fulfills basically one of these three requirements. Boron nitride can actually fulfill all three of them. And so the idea was that then this boron nitride would just act as an inert substrate. We could put our graphene on it, and we'd be all set with that. And so this is the first results from the Kim group here, looking now at resistance as a function of gate voltage. And what you saw on the previous slide here, this is a very wide peak in gate voltage or in charge density. Uh-oh.
Yep.
Here it became very narrow now in gate voltage or in charge density. This is already a sign that there's much less disorder in these samples. It takes a very small gate voltage to switch from, say, N to P type. There's not much disorder in the sample. So these are global transport measurements looking at this effect. But we want to actually go and look at this locally to see what's happening on the atomic scale. And so the way that we can probe this is by doing a spectroscopy map over the substrate. We go to each position on the sample, and we take one of these DI/DV spectra. And so these DI/DV spectra can tell you about the doping in the sample just by where the minimum is. The minimum in the spectra is occurring at the charge neutrality or the Dirac point. And as you move to different locations, those minima shift. Here it's a little bit to the left side. Here it's neutral. Here it's to the right side, etc. And so we just map the shift of this Dirac point as a function of position in the sample. And that tells us something about the charge disorder in the sample. And so we did that for a series of different samples. So this is a graphene on silicon oxide on the left-hand side. In the middle, we've put in a 15 or so nanometer piece of boron nitride. And in the right-hand side, we've put boron nitride with a graphite gate and then silicon oxide underneath. And so the color scale here is giving you the fluctuations of this Dirac point, these potential fluctuations. And so this is a typical silicon oxide sample here on the order of about 50 MeV fluctuations in the Dirac point. If you move to having the boron nitride, it's reduced by about a factor of 10, but the spatial extent is also spread out of the charge fluctuations. And that's because all you're doing is you're basically displacing the charge traps that are here at the silicon oxide substrate, displacing them away from the graphene. So they become weaker in intensity, but since they're further away, they have a larger spatial extent. If you instead use a graphite gate here underneath, so graphite being a metal or a semi-metal, can screen all of the charges which are sitting in this silicon oxide. And what you see here is essentially a white display, which has basically reached the noise level of our measurement.
So have you checked, when you use graphite gates, have you found a correlation whether the HBN is thicker or not? Because there's some evidence lately coming up from basically thick HBN. You don't need graphite underneath. It gives you everything that you want, which is just be far away from the. Do you know if the graphite for sure helps, or it's more the thickness of the HBN that does?
I mean, I would think that thick HBN should work just fine as well. So.
Or in other words, have you done thin, same?
So this is thin HBN, relatively thin graphite. So it could be that you use thin HBN and graphite, or you use thick HBN, you get the same result. The one issue I think with using thick HBN is HBN does have defects in it, right? So they're much lower density, but they are present. So when you start using too thick of HBN, you sometimes see the defects in the HBN instead, whereas I think if you go here, you're probably going to, in general, have a better results because you're only 10 nanometers of HBN. Right? So I think actually this red dot here may actually be a defect in the HBN and not from the silicon oxide. All right. So this is basically showing that using the HBN did exactly what we wanted. We got us much better, cleaner graphene devices without having any modifications to the graphene's properties. And if you go and look now at the sort of atomic scale images here, you can get very nice atomic resolution images of the graphene lattice because it's now sitting on a very flat substrate. Before it was on this very bumpy oxide, it was hard to see the lattice. But here we get nice atomic resolution. But if you go and zoom out a little bit here, you start to see these Moiré patterns. So there's these larger scale Moiré patterns which form. And so here you can see there's like a 1 nanometer Moiré pattern. The little black dots are the atomic scale lattice. If you go here, there's about a 2 nanometer Moiré pattern. And so depending on the sample, you have a whole range of different Moiré patterns that are forming. And all that this is arising from is the fact that the graphene and the boron nitride have the same lattice, or essentially the same lattice, slightly different, and that there's a twist angle between them. So we have here the boron nitride. We put the graphene on top of it. You put it on top with a 5-degree twist angle, and you see this Moiré pattern here, here, here. If you go and put it with a 10-degree twist angle instead, then you see a pattern here where the Moiré pattern gets shorter. So just by controlling the twist angle between them, you can get different Moiré patterns. And so here's what happens as you maybe, nope, guess it doesn't want to rotate.
It did rotate a little.
It did? There we go. So as you rotate it all around, you see them match up. You get a very long wavelength Moiré. As you get them about 30 degrees apart, you get a very short Moiré, and then it grows out here, and you can see a sort of twist as you go. Because the lattice constants have slightly different lattice constants, there's a maximum of about 13, 14 nanometers that you can get here on the Moiré pattern. And so what we've seen here is that just by changing the twist angle, we can get all of these different Moiré patterns. And it's pretty simple to work out what the wavelength should be. It depends only on 2 parameters. One is delta, which is the lattice mismatch between the graphene and the boron nitride. And the other is phi here, the twist angle between them. So we have no control, essentially, over delta. Right? The 2 lattices are what they are. But we can control phi. And just by changing that, we get these different Moiré patterns. And so we go from 2 nanometers to 6 to 11.5. And you can see already here that the Moiré pattern, sort of what it looks like, is changing as we change the wavelength. It's becoming a little bit sharper here on these boundaries, which I'll come back to in a few slides, on what's happening in these very long wavelength Moiré patterns. But I just wanted to spend an interlude for just a minute spent on this superlattice potential that's arising here. And so because we have this Moiré pattern, right, that does mean that there is some interaction between the graphene and the boron nitride. It's not actually acting as sort of an inert substrate. There is an interaction there with some periodicity given by the Moiré pattern wave vector. And that's going to then cause the normal Dirac cones to get these new superlattice Dirac points at a wave vector that's associated with the Moiré. So by changing the rotation angle, that changes the wave vector here. That moves it up or down in energy. And you get these new dips in the density of states as a function of energy. And so these are calculations for 6, 10, 12 nanometer Moiré patterns. The density of states, instead of being nicely V-shaped, gets these new dips here from the superlattice. And so this was calculations. And then we went and did some experiments here on a couple different wavelengths. And we see this same dip here and in the density of states. And to see it a little bit more clearly, This is a color scale where the color now is the density of states as a function of gate voltage. So we're tuning the charge density in the sample. The Dirac point just moves like this, moves on this square root of the gate voltage. And there's this superlattice Dirac point, which just moves parallel to it right here. And so these two are always a fixed energy apart. So that's how we know that the dips that we're seeing in this spectroscopy are actually a band structure effect and not coming from some other thing. They're moving always in parallel here. And from this, you can read off the energy of this dip. So this one is like 0.25 electron volts or 0.3 electron volts away. And so from that, then, and this 9 nanometer Moiré, those two pieces of information are all you need to know about for the wave vector. And so we plotted that energy as a function of wavelength or inverse of the wave vector, and we found this nice 1 over wavelength. It's linear with the wave vector. So this shows that essentially that the boron nitride is having an effect on the sort of high energy properties of the graphene. These are occurring, minimum 0.2 eV away from the Dirac point all the way up to 1 eV away. But we can't actually access anything lower than this because the longest wavelength you can get for this graphene on boron nitride is this 14 nanometer wavelength. And so you can't get any longer wavelengths because of the lattice mismatch. And so we're interested in seeing, what other properties can we modify at lower energy in the graphene with the boron nitride. And so ideally what we would like to do is break the inversion symmetry of the graphene and actually open up a band gap in it. So here we have our normal Hamiltonian, which gives the Dirac spectrum here. But if we can break the symmetry, we could open up a band gap in the graphene. And so this Berry curvature would be non-zero, and we could do interesting things like the Valley Hall effect. So we need some way of breaking this symmetry here in the graphene. And so the way that we can do this is by matching the graphene to a lattice, a substrate, where we break the symmetry between the A and the B sites here. So these two carbon atoms right now are seeing the same environment, but if we can make them see different environments, we can break the symmetry here and open up a band gap. And so that's where the boron nitride can also come in. And so there was this early report from Manchester group here about the possibility of making the graphene be commensurate with the boron nitride. So the graphene lattice constant is 1.7% smaller than the boron nitride. And so their report here was that there was some transition at certain long wavelength Moiré patterns where they saw different things in their AFM, which they claimed then was a sign that the graphene and the boron nitride were becoming commensurate. And then beyond that, there were transport measurements, which showed the same type of thing where a gap was opening. So this is work from Pablo's group here, looking at very long wavelength. You can start to see band gaps on the order of room temperature, 300 Kelvin. Also from Corey Dean's group, where they see band gaps opening on the order of about the same 25, 30 MeV. And so what's happening here in these very long Moiré patterns is there is some evidence that there is a band gap opening. There's some breaking of the symmetry. And so we wanted to go and look at what's happening locally in these samples. And so the way we went about trying to probe this was by taking advantage of the sort of last degree of freedom that we have, which is the separation between the tip and the sample here. So we're changing the bias current, we're changing the imaging conditions here, and we're working in this case with our tip very far away, so it's essentially very low current. And as you increase the current, you bring the tip closer and closer to the surface. And so this is the same exact area of the graphene substrate, and all we're doing is changing the imaging conditions. And you can see that the Moiré pattern that we have changes quite dramatically just as a function of this tip sample separation. So we go from a smooth Moiré here to these very sharp lines here. And so this sort of brought to mind some work that had been done on what should happen. These are just calculations of what should be the adhesion between graphene and boron nitride. So if you have just unrelaxed graphene, just put graphene on boron nitride, you should have something like this. But if you start to make it locally commensurate by straining the graphene, then there gets to be changes here. And if you start straining it quite a bit or putting a lot of adhesion, so 1 electron volt per unit cell, you get these very sharp lines here. So the graphene becomes nicely matched here, and there's these domain walls that form on the edge of the Moiré. And so to us, that looked a little bit like what we were seeing here in our STM images. We went from some kind of smooth landscape to a much sharper landscape over here. And so we wanted to actually go and see, do we actually see this strain in the graphene? And so the
difference in the top row is only the distance of imaging?
Yes.
What's that got to do with the strain of the sample below?
So I'll come to it. The tip is basically interacting with the graphene and changing the interaction with the substrate. So we want to go and actually measure the graphene lattice constant to be able to see if there's strain in the sample. So we wanted to go and map out throughout this thing what does the lattice constant look like. So we go and take a little box here, this white box. We take a high resolution topography image there. When you do that and take a Fourier transform, you can go map the lattice vectors of the graphene. So we have the lattice vectors there. We measure the length of them. That'll give us the lattice constant. And now we just take this box and we take the same measurement all over the sample. So we map the entire area. And so for each point that the box is, we get one number, which is the length of the lattice. And then we plot that number for every position in space. So for the box here, we got a length of the lattice here. We do it the same thing everywhere in the sample. And we're measuring here the measured lattice A relative to the sort of unperturbed graphene lattice. And so what you'll see is that there's definitely variations here. There's some parts which are smaller, 0.97. There's some parts which are longer for the graphene lattice. So there's a spatial variation in the graphene lattice. And if we take this data now and we just look at 1 unit cell and take a little higher resolution, what you see here is that in the center of the unit cell, the graphene lattice is expanded. So it's 1.02. And that means that the graphene is matching the boron nitride in the center there. And then it has to relax along the edges of these domain walls to keep the overall lattice constant fixed, the overall area of the sample fixed. So we're stretching in the center and relaxing along the outside.
Sorry, Brian, this was under which imaging condition? The one that where you're pushing strongly?
This one is the middle imaging condition.
Okay.
So these are the results for the 3 imaging conditions. This was the one that I was just showing, roughly the same one. If we don't push very strongly, there's actually a very weak effect here. There is still some effect. You can still see a slight variation, but it's on the order of 0.2, 0.3% or something. If you start pushing stronger here, that's when we can get basically this full 2% lattice strain. Here, this is an imaging condition where we're pushing really hard. And so you can see kind of crazy things happening here in terms of the topography. And so there's, this is actually a hysteretic regime. It looks different forward and backwards. So we're actually really affecting the sample here. But you could see we could get very large strains just by.
Opposite sign as when you were moderate.
Yes, they flip signs, which we've never been able to understand exactly why. There was it's probably a measurement problem that we're stretching the thing out and losing some of the measurements here. OK, so back to Rick's question on why is this happening? How is this going about? So if you have just graphene on boron nitride, there is a slight preference for the carbon atoms to sit over boron atoms. It's a little bit lower energy state there. And so the graphene wants to slightly expand to match the carbon with the boron in some region, and then it contracts here when the carbon is over the nitrogen sites. So there's already this slight lattice distortion. And now there's an interaction between the tip and the graphene. And we can be in different modes. We can be in the mode where we're far away from the substrate. There's a van der Waals interaction between the tip and the graphene, which pulls the graphene up a little bit. And so essentially, when that occurs, the graphene doesn't see the substrate as much. So it loses this matching to the substrate. And then everything becomes back either to the normal graphene lattice constant or something near there. When you press down with the tip, so you get very close to the sample, you're basically changing the gap between the graphene and the substrate. That's going to enhance the interactions between the two, and it's going to favor this carbon over boron. So it's going to want to make a commensurate matching under the tip. And so the graphene lattice will strain when you're pressing down on there. So this is with the tip, it's this position. Here, the graphene lattice becomes slightly strained underneath it, and so we see a longer lattice constant when we press down hard than when we're either far away or if we could do the measurement without being there. And so this was calculations here showing the expected strain field that you should get here in these different imaging conditions. These are our experiments here. These are the calculations of what you should expect to see. And so you can see that when the tip, this was condition of the tip being far away, there's a slight variation, and that's just coming from the natural sort of matching between them. Here's when you're pressing down hard, we get pretty good agreement between them. When you're pressing down very hard, as I said, this is being hysteretic, and the calculations expect to have a very large contraction along the domain walls. We don't see that, and I'm not sure, if you should really take too much away from the fact that we don't see the same there. But the main takeaway are on the two ones on the left here. When you make a device, if you don't do anything to it, you have this small strain between it. If you can somehow push the graphene down into the boron nitride, you can enhance the strain and get a better lattice matching between the two materials. And so there was some subsequent work on this by Corey Dean's group using pressure cell. So they put the graphene on boron nitride in a pressure cell and just increased the hydrostatic pressure, which is essentially the same thing as pushing the graphene down with the tip. And so what they saw there, this is the function of pressure. This is the gap that was measured at the Dirac point in black. And so they see that the gap increases at the Dirac point as a function of pressure. And so this is the same explanation, that when you press it down, you're favoring the graphene stretching to match the boron nitride. When it does that, it becomes commensurate, or at least somehow locally commensurate with the boron nitride. And so that then starts to open a band gap because you have an asymmetry between the carbon atoms which are sitting over the boron sites and the carbon atoms which are sitting over the center of the hexagons. All right. So that was, yeah?
So it seems like your picture has this autoplane modulation in graphene lattice.
Yes.
So is that coming from your measurement, or can you prove that autoplane modulation scale in your measurement somehow?
Yeah, so unfortunately with the STM, you don't really get true topography information because there's always the integral of the density of states on there. So there is an autoplane signal, right? There's a delta Z signal that we see, but we can't be certain that it's a pure topographic and it isn't also a density of states which is causing the tip to also modulate. So the calculations say that there should be a small autoplane, and we see an autoplane, but I can't guarantee that it's not an electronic effect on top of a topographic effect.
Did you do this in your AFM?
I did not do it. We tried to do it in an AFM, but so my AFM doesn't have high enough spatial resolution to do it. We sent the samples to someone, but we weren't able to get good data.
Another naive explanation would be if the graphene might attract the tip, right? And it wouldn't these things.
Oh, yeah, so they're attractive. They are attractive.
So why does it push down instead of pulling up?
It can do both. It just depends on what tunneling conditions. So the ones on the left, we could actually pull it back, or you could push, leave it basically at its correct height or push it down. And you can see that if you just do I versus Z, you can see when you're pulling it up, when you release it, and so you can figure out what imaging conditions you're in.
Maybe you have data. What happens when you approach a defect? You start doing the same imaging.
Yeah, we don't have data on that. So most of these graphene boron nitride, it's very rare to find any defects in them. And so, yeah, we just haven't seen.
Well, you could make them.
We could make them, yes, but we haven't done that. So the other story that I wanted to tell you was what happens when you do graphene on graphene. So as you probably know from Pablo's work, when you take the 2 layers of graphene here, you put them with a twist angle between them, you can change both electrical and optical properties. Right? You're just basically changing in K-space where these cones are, and if you get them close enough together, you get these flat bands and you get these superconductivity at 1.1 degrees or so. So we were interested in looking here at just a range of twist angles, and so we had developed this technique for basically making controllable rotations between the different layers. And so the idea here is to take a large piece of graphene here, and then we come down with our stamp to make this heterostructure, and we pick up just the left or the top half of it in this case. So you rip that off, you then have a small twist angle between them, and then you pick up the second half here. And so this was work done in Emmanuel Tutuk's group, developing this technique to make these heterostructures where we can have a controlled twist between the 2 graphene layers. And since they're coming from the same graphene flake, we know precisely what the angle is just by how much we rotate the stage between the two transfer steps. And so we looked at this now just from a topography point of view. And so what you see here is we have the wavelength as a function of these 2 parameters here. Again, delta, the lattice mismatch between them, and phi, the rotation angle. And in this case, because we're using 2 layers of graphene, delta is 0. And so this equation simplifies to something which just depends on the rotation angle between the 2 lattices. And unlike the boron nitride, there is no limit to how large of a wavelength you can make. Right? If you make phi go to 0, this thing becomes infinite here. And so if we look at the wavelength as a function of the twist angle, it just diverges here at 0 twist angle. And so here are some examples of Moiré patterns that we've measured in this graphene, twisted bilayer graphene case. So this is about a 5 nanometer Moiré. This one is on the order of 20 nanometers, and this one is on the order of about 50 nanometers for these Moirés. So this corresponds to something like 0.2 degree rotation angle. I think this one is about 0.6 or so degrees rotation angle. And so you can get these very long Moirés, something that's just not possible in the graphene on boron nitride case because you have the same lattice constants. And so here, if you look, there's a slight difference to what happens here when you twist them. So before you saw when they twist it, the whole pattern kind of rotated with twist angle. This one just goes in and out. And so the orientation of the Moiré pattern with respect to the graphene lattice is very different in this case of graphene on graphene than it is on graphene on boron nitride. And so you can see here as it gets very long, it stays aligned with the graphene lattice here. And so when that's happening, there are going to be regions in this long wavelength Moiré pattern which have AA stacking. So the 2 lattices directly on top of each other. There's going to be regions which are Bernal stacked, AB, and also BA here. And so in our measurements, we're going to have all of these different regions which are going to be in the sample, and they're just going to be spatially separated. And we're going to apply an electric field from the tip and the backgate voltage. So we have our sample, we apply a voltage on the tip, a voltage on the backgate, that's going to apply an electric field. In Bernal stacked graphene, when you apply an electric field, you open a band gap. So that's these dashed red lines. And the strength of that band gap just depends on the magnitude of the electric field. However, in this AA stacked region, when you apply an electric field, nothing really happens. You remain still in the same dispersion relation. There's no band gap opening. And so we're going to use this fact that we have different behavior with electric field to try to induce new topological states in the graphene. And so we can also look at that if you had just Bernal stacked graphene, and instead of applying a constant electric field, you apply an electric field which rotated from out of plane to in plane. There would be band gaps on the left-hand side and the right-hand side because we have an electric field on both sides. And here in the middle, where the electric field is 0, where it's rotating like this, at some point it's going to be 0. And in that point, there would be a conducting, a non-insulating region of the sample. That's equivalent to applying a uniform electric field by going from AB region to a BA region. If you just change the stacking configuration but leave the field profile the same effect will happen. You'll have a gapped region here, a gapped region here, and a conducting region on the inside. And so there's been calculations, I guess, 5 years ago here on these systems. In the bulk, we have this gap state, and there should be 2 conducting channels moving along the boundary here, and they are moving opposite directions in the K and the K prime valley. So these are topologically protected states at this interface here between these stacking configurations or along the 0 line of the electric field if you had uniform stacked graphene. So in our case, we have these long wavelength Moiré patterns, and so we have well-defined AB and BA regions. And then between them, there are these dark lines here. These are domain walls. And they are connecting the AA stacked regions, which show up as a bright spot in our STM measurements. And so we have AB, BA alternating around with the AA in the center. And so we naturally get these domain walls in our sample. And so the idea then is to go and do spectroscopy and look at how the spectroscopy varies at the different locations in this unit cell.
So what's the color scale for this one?
This color scale is the Z channel from the STM. So again, it's an electronic. Here it's almost certainly an electronic effect. And so here you can clearly see that the convolution between the electronic and topographic effect in the STM.
And which conditions are you mentioning?
This is no gate voltage here. So this is relatively far away with the tip, as we weren't trying to be invasive with the tip here or anything. Of course, the tip always is an invasive probe of some sense, but this was trying to be non-invasive. And the back gate at 0 here. But the back gate doesn't really, I should say, there's not much effect if you change the back gate voltage. You get basically the same picture for all back gate voltages. Yeah? Do you know which one is BA or AB? We don't really know. They have to alternate going around. It turns out that AB and BA, when you do the spectroscopy, the 2 regions are going to be identical. So we can't actually tell. So we went and did the spectroscopy around each of the different areas here. So you have AB, AA, and then this is along the domain wall region. And so what these plots are showing, the color scale is density of states. It's as a function of energy here, and then this is backgate voltage. So the backgate voltage is controlling the electric field in the sample, and the dark is low density of states, the bright is high density of states. And so what you see here in this Bernal stacked, we started basically charge neutrality point here. As we increase the electric field, this black region is getting wider in energy. We're opening up a band gap here at high gate voltage here in the Bernal stacked. So the BA region looked identical to the AB, so I didn't show it here. In the AA region, there's these states here that kind of move around, so there's some interesting things happening, but the main point is it stays conducting all the time. There's no band gap opening there. And the same thing is happening on the domain walls. There are states that move with energy, but it's also remaining conductive. And so to look at this a little bit more clearly, instead of just taking spectroscopy at fixed locations, we went and mapped local density of states. And so we took local density of states measurements inside and outside of the band gap here. And so if you go outside of the band gap, so this is at high energy, everything is conducting, you see essentially a uniform density of states on the regions other than the AA sites. So on the AB and the domain walls, it's essentially a uniform density of states. So the electrons can move freely everywhere there. If you go inside the band gap, so you use a condition where you've opened a gap in the Bernal stacked region, you use low bias to probe in there, what you'll see is the dark regions here and the Bernal stacked regions, they have low density states, they're gapped. And there are these two lines that connect along each of the AA vertices. And so these are these topologically protected states which are running between the AA sites along the domain walls. And so they appear here, always connecting the AA sites. And we only see these states when we get to these very long wavelength Moiré patterns. So at the sort of 1 degree twist angle where the Moiré pattern is like 10 nanometers or so, these states don't appear. It's only when you get down to about half a degree or smaller, so something on the order of 30 to 50 nanometer Moiré patterns, that these topological states appear, because you need to have well-defined domains of Bernal stacked with the domain walls in between them. If you go to a smaller twist angle, you don't have these well-defined domains where you can see the differences. Yep.
Have you checked a little bit this pushing dependence of all of this?
We tried the same kind of things that the HBN, and we didn't see much going on here. We never were able to see the same kind of strain effect. And we tried that same thing of just graphene on silicon oxide and weren't able to do it there. There seemed to be something special about the boron nitride.
But you might expect a similar effect for graphene on graphene, right? In terms of
Yeah, I think it's definitely possible here. Yeah. But
you can map the relaxation of the lattice.
Right, but there's not a reason for the lattice to stretch here, right? Because
No, yeah, because it lacks more AB than AA.
yeah, but that's still a lattice constant that's the same, right? So there should only be stretching in like certain areas here. Like this whole region here should be just normal graphene lattice constant.
Yeah, but there are calculations.
Yeah, no, I know. Yeah,
I mean, I'm sure you're aware. So have you tried to map to see?
Yeah, we tried it and we saw nothing.
Okay.
So that is inconclusive, right? It could be that it's too small to measure. It could be lots of reasons. Right? So today I told you graphene on graphene and graphene on boron nitride, but we've also looked at putting graphene on a semiconductor. This is tungsten selenide. Here's graphene on a superconductor. So this is graphene on niobium diselenide. And then we put a small magnetic field. And so these are the vortices which show up in the niobium diselenide. Graphene on bismuth selenide. So other things. So my group is looking sort of a whole range of these different graphene heterostructures and trying to explore new physics in those. And so what I've told you about today is essentially by tuning these three parameters, some new things that can emerge in these van der Waals heterostructures. So by tuning which materials you're using, their rotation between them, and also by tuning their interlayer separation. So if you can get away from this sort of equilibrium separation, you can induce new effects in those. And so I should, before ending here, thank all the people who really do the work, because it's not me, it's my grad students in my lab. So they've done all of the measurements and done all of the work. And also lots of collaborations with Pablo for making samples, also with Emmanuel for samples as well. Boron nitride comes from Japan, and then Alan McDonald and Pablo San Jose for the theory portions. Pablo did the theory on the graphene on boron nitride, the relaxation there. Alan did the theory on the graphene, the twisted bilayer graphene. And thank you for your attention.